Hi everyone, I'm Anna Ha, and this is my Physics 2 Lab 1 presentation on charge tapes. So this was our first experimental lab in the course, and the goal was to get really comfortable with the idea that charge is a real measurable property of matter, even on everyday objects. We also focused on designing a simple experiment, making reasonable assumptions, and estimating quantities instead of trying to get an exact answer. So the main goal of this lab was to observe how charge tapes interact and then to use those observations to estimate how much excess charge is on one piece of tape. We looked at both repulsion and attraction, and then I used a floating tape setup to turn what we saw into an actual calculation. Using that setup, I found that each tape had a charge of about 2.2 times 10 to the negative 8 coulombs, or around 22 nanocoulombs. That number might sound small, but I'll later show you why it's actually a pretty reasonable amount for something like tape. So in order to do the experiment, we used really basic materials, clear tape, measuring tape, a flat surface, and 2 thick books that you can see on the right. To prepare the tapes, we first made a base tape and then placed a second strip on top of it. And then while the tapes were still together, we rubbed along the slick side to neutralize the tape pair. And then this step is important because it ensures that the total charge is 0 before separation. And then the actual charging happens when the tapes are pulled apart quickly, which transfers charge between them. And then after separating the tapes, we handled them only by using the ends so we wouldn't discharge them before the measurements. And then these are the key measurements that I took. So the tape was 7 inches, and then when 2 U-tapes were prepared the same way, one tape was able to float above the other at a separation of about 2 inches. And then when I brought them closer together and moved the top down to the bottom, the tape snapped and stuck when the top one was about 1.1 inches from the bottom. And then all of these distances were measured from the top of the block where tape A was fixed, and then tape B was lowered until it either floated or stuck, and that reference point stayed consistent. So the physics behind this lab is actually pretty simple once you break it down. When the tape is floating, it's not accelerating up or down, which means the net vertical force is basically 0. That's straight from Newton's second law, and then there are 2 main forces acting on the tape. 1, the gravity pulling it downward, and 2, the electric force pushing it upward. So the electric force comes from Coulomb's law, and gravity is just mass times gravity. So when those two balance, the tape floats. So to calculate the gravitational force, I first needed the mass of the tape. So the lab instructions say that the clear tape has a mass of about 1 gram per meter, or 0.001 kilograms per meter. And since my tape was 0.1778 meters long, the mass came out to about 1.78 times 10 to the negative 4th kilograms, and then I multiplied that by gravity, and I got the gravitational force of about 1.74 times 10 to the negative 3 newtons acting downward on the tape. And then even though both tapes exert electric forces on each other, I analyzed the top floating tape as the system. The bottom tape is supported by the books and desk, so it has additional forces acting on it that I didn't measure. So focusing on the top floating tape let me set the net vertical force equal to 0 and directly compare the electric force to gravity. And then at the moment the tape begins to float, the electric force upward is about the same size as the gravitational force downward. Lab 1 tells us to make 2 simplifying assumptions. 1, that both tapes have about the same net charge, and 2, that each tape can be treated like a point charge at its center. So with those assumptions, I used Coulomb's law, and I solved for the charge using the measured floating distance of 2 inches, or 0.0508 meters, and that gave a charge of about 2.24 times 10 to the negative 8 coulombs on each tape. So to make that number more meaningful, I converted the charge into a number of electrons. So dividing by the charge of 1 electron gives about 1.4 times 10 to the 11 electrons. And that sounds huge, but when you compare it to how many atoms are actually in the tape, it's tiny. So then using the atomic length scale given in the lab, I estimated about 3.4 times 10 to the 17 atoms on the sticky surface of the tape. And then the ratio of missing electrons to the atoms is about 4 times 10 to the negative 7. So in other words, way less than 1 in a million atoms actually had to give up an electron to produce this effort. I also used a glow script model to support the calculation. So in the model, each tape is represented as a point charge at its center, and the electric field is calculated using the same vector approach we learned in Lab 0. Gravity is included, and the floating distance is used as the separation. The model closely prints out the force and the charges, and the result matched the hand calculation really closely, which helped confirm that the estimate made sense. There are definitely assumptions in this lab. We assumed both tapes have roughly the same charge because they were prepared in the same way. We also ignore air resistance, swinging, and the fact that the charge probably isn't perfectly distributed along the tape. But the lab is only asking for an order of magnitude estimate, not an exact value. And for that level of accuracy, these assumptions are pretty reasonable. And then humidity in touching the tape also affects the results, which is why careful handling was emphasized so much. The inverse square relationship explains why the tapes behave so differently at different distances. When you move from 2 inches to 1.1 inches, the electric force increases by a factor of a little over 3, and that's why the tape snaps into contact at the smaller distance instead of continuing to float. So the experimental observations and the physics model actually line up really well. And then overall, this lab showed that everyday objects like tape can carry a measurable amount of electric charge, even though only a tiny fraction of atoms are involved. By combining simple observations with Newton's laws and Coulomb's law, I was able to estimate the excess charge on the U tape to be about 2.2 times 10 to the negative 8 coulombs. And then this lab was a good introduction to experimental electric forces and how modeling helps turn observations into actual numbers. Thank you.